All right, guys, today's lesson is on equilibrium. Says, hello, Batman. Last time he takes disguise tips from Superman. You guys ever watched the old Superman and pretty much looked the exact same? Clark Kent and Superman looked the same, he just had glasses on. Yeah. All right. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. So we're talking a reversible reaction that can go both ways. For example, it says, since in a system at equilibrium, both the forward and reverse reactions are being carried out, we write its equation with a double arrow. So you'll be able to identify a reversible reaction when you see an arrow going in the right direction and then one going in the left direction. And you can have this when you have something in a closed system. What can happen is, for example, N2O4 molecules, right, can collide together and break up into NO2 molecules. You guys see for every one N2O4 can break up into two NO2s. But at the same time, in a closed system, remember these are gases, right? Wouldn't you expect NO2 molecules could collide, and if they had enough, if they met the activation energy, they could recombine back into N2O4. So what's happening is you have the forward reaction, and then you also have the reverse reaction, okay? And what you'll notice is, you notice there's rate here and time here. So now, look at here, talking about the rate. You guys remember the rate is equal to a rate constant times the concentration, right, if it was first order. Now you guys look, notice N2O4 is our product. So let's say we start with a certain amount of products. You guys can imagine over time as the reaction progresses, what's going to happen to the amount of products? Aren't you going to get less and less as you begin to produce, what's going to happen to the amount of the reactants? You're going to get less and less as you produce more products. So what's going to happen is if you have less N2O4 molecules that are present to collide with each other, wouldn't you agree that that forward reaction starts slowing down? That's what this is showing right here. The forward reaction is slowing down. And then now look at the reverse happening. But then you think about the reverse reaction as this breaks up and forms more NO2, and then you start having a higher concentration of NO2 molecules. And if you have a higher concentration, wouldn't you guys agree the frequency with which those collide would be greater, and therefore you would expect the reverse reaction to speed up? That's what this is showing. And hopefully you guys can see from the graph, eventually, wouldn't you guys agree, eventually you're going to reach a point at which what? The rate of the forward reaction is equal to the rate of the reverse reaction. And as you guys might guess, that's what we call equilibrium. At equilibrium, the forward and reverse reactions are proceeding at the same rate. Notice that you guys remember, I always encourage you guys to write down at least what I put in purple. It's up to you. You guys can write down everything. You don't even have to write down what's in purple as long as I get some video notes from you guys. And you'll notice, right? So then the rate just proceeds. The rate of the forward reaction, the rate of the reverse are at the same speed. Now, you guys, the reason why this graph looks different. Notice the vertical axis here. That now it's concentration over time. Okay. Before, you guys remember it was rate over time. Now it's concentration over time. Once equilibrium is achieved, the amount of each reactant and product remains constant. So now look, concentration. You guys remember this was our reactant N2O4, and obviously the concentration goes down as it proceeds, right? But once it reaches equilibrium, the amount of N2O4 stays the same, and here's the reason why. Because right, as that reaction was progressing, wasn't the NO2, which was the product, wasn't its concentration increasing as more and more N2O4 broke up in NO2? But then, right when you think about it, so eventually we reach, right, equilibrium, where the rate of the forward is equal to the rate of the reverse, right? And if that's the case, wouldn't you guys agree? If you have just as much going this way as going this way, wouldn't you guys agree that the concentration of both of those at equilibrium would remain constant, right? Because you have just as much of this being produced as is being used up, and just as much of this is being used up as is being produced. And so what will happen is the concentrations will stay constant. You guys, it's very, very important to realize though, when we say equilibrium, the question is what's equal? What's equal is the rate of the forward reaction is equal to the rate of the reverse reaction. You notice what is not equal? The concentration of your reactants and products, right? So that's not what equilibrium means. So in this case, what side is favored? Wouldn't you guys agree? This side is favored because at equilibrium, I'm going to have a greater concentration of NO2 than I would have of N2O4. So basically, the atoms prefer to be in this arrangement than they do in that arrangement. Since in a system at equilibrium, both the forward and reverse reaction are being carried out, we write its equation with the double arrow. Okay, so we already talked about that. Okay, so now we're going to introduce what's called the equilibrium constant. Okay, so now check this out. Here's the forward reaction, right? N2O4 breaking up into 2NO2. If we were to write the rate law, let's assume this is an elementary step. So let's just say, right, we put it first order based on this, though you guys remember it is based on experimental data. But you remember the rate law is rate is equal to a rate constant, I'll call it KF for forward reaction, times the constant, and it's dependent upon the concentration N2O4. As you guys might guess, the rate law for the reverse reaction would be the rate constant for the reverse. You guys see, when I did reverse, I just took this and then, you guys see, now I'm going to just write this going to this, right? That's what we're doing here. And then it's going to be second order with respect to NO2, okay? And what did we just say? At equilibrium, so now let's put those together. At equilibrium, what did we say? The two rates are equal, right? The rate of the forward is equal to the rate of the reverse. So then I can take the rate law for the forward reaction and make it equal to the rate law for the reverse reaction. And then what I can do is just kind of algebraically manipulating, putting my constants on one side and the concentrations on the other side. And you guys can imagine, right? So then the concentration NO2 squared over the concentration N2O4. You guys can imagine if you have a constant over a constant. Remember, a constant is a number that doesn't change. Wouldn't you agree that's just a constant? So what I can do is I can just make here. So the ratio of the rate constants is a constant at that temperature, and the expression becomes. So you guys, you see what we do? We say a constant over a constant. We just make it a constant. And we call it the equilibrium constant. So this is what the equilibrium constant is equal to, or if you take the ratio of NO2 squared to N2O4, the ratio will always equal a constant. You guys are going to start seeing where we're able to utilize this information in equilibrium problems. So let's say we have this generalized reaction. Basically, we kind of showed you how we can get an equilibrium expression. Here's like a generic equation, okay? You guys, the lowercase representing the coefficients and the uppercase representing the reaction species. Here's what the expression would be. You take the concentration of the products, and you notice you'll raise it to a power equivalent to the molar coefficient. So you take the products, the ratio of the products to the reactants. What you'll find is, at equilibrium, when you take the ratio of products to the reactants, you'll always get a constant. That's called the equilibrium constant. The reason why we just put a C there is because we're talking about concentrations here. It can be slightly different. Look if we deal with all gases, for example, right? You guys remember when we're dealing with gases, we're usually dealing with the pressure of gases. You guys know the higher the concentration, the more gas you have in a confined space, the more concentrated it is, and then the more pressure. So we could write the exact same expression, but instead of concentrations, you guys remember the brackets mean the concentration, like in moles per liter. We could do it when we're talking about gases in terms of pressure, but it would be the same setup. Hopefully you guys see the same thing there with the previous one. So, guys, let me see if you guys can see this data. Now that'd be really hard, I can see on your end. Okay, so here's what's going on. I'm going to try to bring attention to it. We have different trials here, 1, 2, 3, 4. And so what we do is we have this reaction going on, and we're going to, in a reaction vessel, just imagine we just have, a container, and then we just squirt in N2O4 or NO2, okay? So we're just putting some in there. What's going to happen is they're going to react, and they're going to eventually reach equilibrium. So here's what we do. So for the first one, we put in 0.02 molar of NO2, and we don't put in any N2O4. Once again, if we do that, the reaction is going to go this way, right, initially, but then it's going to reach equilibrium. And so that at equilibrium, we're going to have sum of each. And what we have is 0.0014, 0.0172, okay? And you can see, once again, the concentration of this side, NO2, is greater than that because the atoms, it's more energetically favorable to be in this position, in that arrangement, okay? But then, in a second trial, we put in more NO2. So here we put in 0.02, now we put in 0.03. Once again, it's going to, the reaction is going to kind of shift this way, producing some N2O4, and then it's going to reach equilibrium, and so then we have results here. Notice these values are different than the previous values. But once again, these values here are greater than those values because, once again, the atoms prefer to be in this arrangement than that arrangement. And then we put in 0.04. Once again, it's going to reach equilibrium. And you guys see at equilibrium, we have some of both, okay? And then on the fourth one, it's a little different. In the fourth trial, we didn't add any NO2. What we did was we added N2O4, okay? And then once again, it's going to reach equilibrium, and sure enough, the concentration of this is greater than the concentration of that, which is fine. Now, what I wanted you guys to notice, though, even though, right, depending on how much we use of what we put in, that will ultimately determine what the equilibrium concentrations are, what the concentrations are when they reach equilibrium. Remember, at that point, the concentrations of these stay constant. But I'm hoping what you guys would notice, what do you guys notice here? This says 0.211, 0.211, 0.213, 0.213. Hopefully you guys recognize, even though this is 0.211 and this is 0.213, those are really, really close together. In fact, what you could probably attribute for the difference herein, the very slight difference, is just experimental error. You guys remember, anytime you do an experiment, your data might be slightly off from reality. So for really all practical purposes, these are all the same value. So what do we notice? You notice what it's called? That's the Kc, that's the equilibrium constant. What did we say always remains constant? Regardless of how much reactant you use, how much product you use, what's going to remain constant is the ratio of products to reactants. If I take the equilibrium concentration of the products and I divide it by the equilibrium concentration of the reactants, I will always get the same stinking number every time. That's why it's called a constant. So each reversible reaction has its own unique equilibrium constant. And in this case, for this reaction at 100 degrees Celsius, it's 0.211. And you notice it says at 100 degrees Celsius. What do you think that tells you? What do you think is the only thing the equilibrium constant is dependent upon? Notice the equilibrium constant is not dependent upon how much of each you use, because either way you're going to get the same constant. The only thing it's dependent upon is temperature. That can affect it. So as you can see, the ratio of NO2 squared, because you guys read, look, if we do the equilibrium expression for this, you remember what you do? You take the concentration of the products. You remember, you got to raise it to a power of 2, because that's coefficient of 2, over the concentration of the reactants. So that's what they're saying here. And if you take these values and you plug them in at any time, what do you notice? You get the same stinking number every time, the equilibrium constant. So will the equilibrium constant KEQ ever change? You guys should be able to answer this question I just talked about just like about 47 seconds ago. When will it change? You're like, oh, it won't change because it's a constant. Yeah, if, though, there's a temperature change. So whenever you state an equilibrium constant for a reversible reaction, you have to indicate at what temperature, because depending on the temperature, the equilibrium constant will change. And you guys remember why that is? Because the temperature will have an effect on the rate constant, which does affect, just like you guys know, if you change the temperature, the rate of the reaction will change, and therefore it will ultimately have an effect on the equilibrium constant. Okay. Let's go with this. Oh, okay. So guys, what's the whole point of the equilibrium constant? What does that tell you? You guys, it actually kind of tells you a lot. So let's say you have a reaction, and it just it gives you and you know the equilibrium constant for that reaction at that temperature. What does that tell you? Well, if your equilibrium constant, you guys know right arrow, this is showing when it shows double. Say if it's like greater than 1, or let's say even more, like a lot greater than 1. Let's say it's like 65 or 8,572, whatever. The reaction is product favored. Wouldn't you guys agree? I shouldn't have erased it. Wouldn't you guys agree? Because you guys remember, where do we get the equilibrium constant from? It's the concentration of the products over the concentration of the reactants. So wouldn't you guys agree, if your number here, the concentration of your product is greater than the concentration of your reactant, so the top number is greater than the bottom number, what kind of number are you going to get here? Aren't you going to get a number greater than 1? So what does that tell you? When you guys are looking at a reversible reaction and you see that the K value is greater than 1, what side is favored? When you guys agree the product side has to be favored. That's the only way you're going to get a number greater than 1. And then you guys could probably guess, on the flip side, if your equilibrium constant is less than 1, what does that indicate? Wouldn't that indicate that the reactant side is favored? So for example, right, because the only way you're going to get a number less than 1 is if your denominator is a larger number than your numerator, and your denominator is the reactant, right? So that would tell you that at equilibrium, you're going to have a greater concentration of reactants than products if your K value is less than 1. So the K value does tell you what side is favored. What arrangement do the atoms prefer to be in? Okay, just a few little interesting things about the equilibrium constant. So for example, it says, what notice when you look at reversible reactions? So look, here we're looking at N2O4 going to, basically we just took this reaction, and you guys notice we just flipped it, okay? And really, you could write this reaction either way, right? I mean, if it's a reversible reaction, what's to say that this has to be the reactant, that has to be the product? Couldn't that be the reactant, that be the product? That's what we're showing here. But you realize how you write it will affect the K value. You notice, look, in this case, right, I take the products over the reactants, and then in this case too, I take the products over reactants. If you guys compare those, what do you guys notice? So if I put some concentration values in there, I might get 0.212 for this KC at 100 degrees Celsius. I get 4.72. You guys know what this is? You guys see what this is? When you guys agree that this is just the reciprocal of that, don't I just flip it? You just flip it. So if I want to get the K value, if the K value of this is 0.212, how do I get the K value of the reverse reaction? When I just get the reciprocal of that. So what do? You guys remember what reciprocal is? I just go 1 divided by 0.212. What would I get? 4.72. So it's the reciprocal. So the equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. In fact, a lot of you guys should have a button on your calculator, and it'll say 1 over x. So if you have a certain number, like for example, let's say 5. What's the reciprocal of 5? Isn't it, right? 5, when we say reciprocal, isn't it 1 over 5? So I'm going to put 5 in my calculator. I know you guys can't see it. And I'm going to press the 1 over x button, and I get 0.2, right? Isn't 0.2 1/5, right? 1/5 is 0.2, yeah, anyways. All right. Okay, a slightly different thing here is, let's see. Oh, here's what they did. Now notice what they did here. We have the same reaction, N2O4 going to NO2, but what we did, we just changed the coefficients. Rather than one of these producing 2 of these, you notice that the ratio is still the same. This is a 1 to 2, this is a 2 to 4, it's the same. But that also affects the K value, how that's written. And you guys see what effect it'll have? So you can see we can get the equilibrium expressions from these, both of these. You notice this was 2, and this was 1, and then this was 4 and 2. If you actually work that out, what you'll notice is your K value is just going to be like, so if we doubled the coefficients here, you guys see what effect it has on the K value? It's going to raise it to a power of 2. So if you double it, it's going to raise to a power of 2. You guys can imagine, what if you quadruple this? Instead of a 2, this was a 2, let's say, then you made this an 8. Is that quadruple? Yeah. And let's say this is 1, then you made that a 4. What effects that can have 0.212? Wouldn't it be to the 4th power? So you raise it to a power equivalent to the increase in the factor in the coefficients. That's just something, basically, you can still do all the work and get it, but if you knew that, it would save you from punching in the numbers. Like I wouldn't even have to put concentration values in here. I would just take whatever number this is, and I would square it to get the K value for that. Equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constants for the individual steps. You're like, what? So, it's kind of like this. Right there. What we're saying here is, let's say we have A goes to C, and I want to know what the K value is, right? But let's say I can break up this. You guys remember we have different reaction mechanisms. Remember, a lot of chemical reactions are more than one step. So let's say in reality it goes from A to B, and then the B, let's say it's an intermediate, and then B gets used up and produces C. And you guys can see how the sum of these, right? You guys see that, the work. But let's say I get the K value for this reaction. The K value for this reaction is, let's say, K1, let's say it's 2. And let's say the K value for this reaction, the K2 I'll call it, is 3. The question is, what's the K value for this? You guys see if you guys can read this. The equilibrium constant for a net reaction made up of 2 or more steps is the product. What does product mean? It means you multiply. So what would be the K value, the overall K value? I multiply these and I get 6. So that's just something that you could maybe remember, and it'll actually just save you some work if you just knew, what you do with the K values. All right, guys, we're gonna finish with some problem solving here. Oh, before that, we still got a little more conceptual things. The concentration of solids and liquids are essentially constant. It says if the mass of a solid or liquid doubles, so does its volume. Thus, its concentration, which relates to the ratio of mass to volume, stays the same. For example, guys, let's see, kind of go back to my good tried and true, think about, right, you guys remember we were saying the K values depend, remember when we did the equilibrium expression, it depends on the concentrations of your reaction species. So now let's think about, here, you know what? Let me do this. Sorry guys, I'm gonna get here just a sec. But I think just even a little visual, even if it's really simple, will help you guys. So think about, let's say paper reacts, right? So when you guys agree, paper does have a concentration. We don't really talk about paper with concentration, and here's the reason why, right? It has a certain mass, and it takes up a certain volume. So you could calculate the concentration, take the certain amount per space. Now let's say the paper reacts, right? So a typical reactant, it's being used up. When you guys agree, I have less paper, right? So now, let's, I want to set off my fire alarm. Okay. Now the question is, okay, what happened to the concentration of the paper? When you agree, I have about half as much paper, so I have about half the amount of weight, but when you also agree, don't I have half the volume? So if I half the mass and I half the volume, what did I do to the concentration? When you agree, the concentration just stayed constant. The concentration didn't change. So even though the reaction progressed, the concentration doesn't change. That's the case with pure solids. Think about that with even pure liquids. Let's say I had water. Let's say this is my reactant. So some of the water gets used up. Think about it. Could I talk about concentration of pure water? I guess you could. You could talk about how much you have in a given volume, when you're talking about a pure liquid. But then think about in a reaction, let's say some of the water gets used up. Now you guys think about it. Half of the water, let's say, got used up, but now when you guys agree, it occupies half the volume. So what happened to the concentration of the water? It's still the same concentration. So when it comes to pure solids and pure liquids, the concentrations don't change. So what that means is you will never include those in your equilibrium expression. So therefore, the concentration of solids and liquids do not appear in the equilibrium expression. So here we have, basically, you know what this is kind of indicating? We have lead chloride, which is a solid, and now all of a sudden it's aqueous. You know what this is showing? It's saying we're taking some lead chloride and we're putting in some water, and then some of it's going to, right, you guys remember if it's ionic compound, it's going to dissociate, okay? But at the same time, not only would lead chloride dissociate into this, could the lead ions and the chloride ions come back together and form lead chloride, and it's going to reach a equilibrium within an aqueous solution. So the question is, what is the equilibrium expression? You guys remember what the expression is? It's the concentration of the reactants raised to the corresponding powers, the coefficients, over the concentration of your reactant. But what did we just learn here? So that being said, our equilibrium constant is the concentration of the lead ions times the concentration of the chloride ions. You can remember, you got to raise it to the second power because it has a coefficient of 2. Normally, I'd put it over the concentration of lead chloride. Here's why. Guys, look, let's say I put it over lead chloride. But what do we say it happens to the concentration of lead chloride? The concentration stays the same. It's like the paper. So this is like a constant. So think about it. That's like a constant. It doesn't change. Can't I just bring out that constant here? Right? I can multiply both sides and bring it here. And what's a constant times a constant? It's just a constant. So it's not going to have any effect on that on the expression. So the point is, that all being said, pure liquids and pure solids do not include. So what do you include in equilibrium expression? You include aqueous, right? Those are like ions dissolved in particles dissolved in water, and you also include gases. Okay. Another last conceptual, you guys, this is kind of unique. This is kind of trippy. So here we have calcium carbonate, which is a solid. So we put some calcium carbonate, and what's going to happen is it's going to spontaneously break up into carbon dioxide and calcium oxide. And so, this is what this shows. So here we have some calcium oxide, and then you notice, look what we do. So here we use a lot of calcium oxide, and we use a little bit of calcium carbonate. here we use a little bit of calcium oxide and a lot of calcium carbonate, but you'll notice, what do you guys notice with the carbon dioxide? In both situations, hopefully you guys can see if you count the molecules, the carbon dioxide concentration stays the same. That it doesn't change regardless of the calcium oxide concentration or calcium carbonate. In fact, you guys can see that when you guys do the equilibrium expression. If I was to do the equilibrium expression for this, right, I'm going to put KEQ, or I could put, you could call it KC, you know, because we're dealing with concentrations, either one, equals, right, the concentration of CO2, or, right, and then you guys, what else do I put? Times the concentration of CO? No, because that's a pure solid. Over the concentration of CaCO? No, because that's a pure solid. What's the equilibrium expression? It's just right here. What does that mean? The concentration of CO2 is always equal to a constant. It never changes. As long as I have a little bit of CaO and a CaCO3, as long as I have some of either one of those, it's going to reach this equilibrium, but the carbon dioxide concentration will stay constant. Okay? Regardless of the CaO and CaCO3. Okay. Okay, now we're going to get to some problem solving. It says, I knew an animal experimentation would come back to bite us. So they did these, took over. That's like Planet of the Apes, but like in a more bizarre, trippy fashion. He's got a syringe. That's pretty creepy. Mouse has a gun. Anyways, okay. Calculations, you guys write this down. That's all in purple. You guys, in fact, we're just going to do one problem, and we're going to work it out step by step, so that way you guys know how to do these at home. Okay, what time are we looking at? Are we almost out of time? Okay, I think we can get this. Okay, so a closed system initially contains 1 times 10 to the negative 3 molar H2 and 2 times 10 to the negative 3 molar I2 at 448 degrees Celsius is allowed to reach equilibrium. Notice we give a certain temperature because that you're going to have an equilibrium constant at a certain temperature. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative 3 molar. Calculate the Kc at 448 degrees Celsius for the reaction taking place. So here's the reaction, okay, so I wrote it, okay. So then the next thing I want us to do, what we're going to do is what we call an ICE table, guys. You guys, you have to get this down. Anytime you have an equilibrium problem, you do what's called ICE. ICE, here's what it stands for. I is your initial, C is your change, E is at equilibrium, okay? So, looking at that information there, it says a closed system contains 1 times 10 to the negative 3 molar H2. Oh, you know what? That's how much I have initially. I got 1 times 10 to the negative 3 molar hydrogen. I have 2 times negative 3 molar iodine, 2 times negative 3 molar iodine. These are all initial. It's kind of understood that those are my initial concentrations. The fact that it doesn't mention HI, what do you guys think that tells you? Initially, right? So here's what we do. We have this container, and I'm putting in some H2 and I'm putting in some I2. Okay? And what's happening is some of that is going to combine together to form HI, but it's a reversible reaction, so HI will also be breaking up to this, and it's going to reach equilibrium, right? So then at equilibrium, I'm going to have some H2, I'm going to have some I2, and I'm going to have some HI. So initially, though, I don't have any of the product, right? And then it says, let's say it's reached equilibrium. How are we going to know it's reached equilibrium? Because all of the concentrations stay the same then, okay? And if it has a color, some of these have a certain color, like iodine would have a certain color, it's like a purple. If I view my box, which has all these gases, if I see the colors just now remaining constant after a certain amount of time, I realize, oh, all the concentrations are staying the same, it's reached equilibrium. And then let's say we're able to separate them, and we find out that the concentration of HI at equilibrium is 1.87 times 10 to the negative 3. So what am I going to do? At equilibrium, I'm going to put 1.87 times 10 to the negative 3. So this is our ICE chart, right? Initial, change, and then equilibrium, ICE. Okay, so we have that. So then think about it, guys. If initially I had 0, and now at equilibrium I have 1.87 times 10 to the negative 3, what was the change? Would you guys agree it just has to be plus 1.87 times 10 to the negative 3? Right, because obviously I had none, and then I gained this much, so then that's how much I had at equilibrium. Now you guys look, here's where you guys use the coefficients. Remember what the coefficients tell you. It says one of these reacts with one of those to produce 2 of those. So if I produce 2 of these, I must use one of those and one of those. But how many of these did I produce? 1.87 times 10 to the negative 3. So how much of this got used up? When you agree half of this. And so they already did the math, so that's plus 1 point. So what I do is I take this and I divide by 2 based on the fact that it's a 1 to 2 ratio. And what I get is, and you notice it's a negative because that's how much was used up because it was my reactant, right? So basically, just to be clear, guys, just to be clear, this value here is this value divided by 2. And then, so how much would I then have at equilibrium? What am I going to do? Well, this is how much I had initially. This is how much reacted to form this. So what do I do with these? When you just subtract it and you get this. Okay? So now I have, these are all the values here. This is my hydrogen, this is what I have in equilibrium, this is my iodine, and this, you notice they're all together now. Okay? And what you guys should notice is, this value is larger than any of these values. Hopefully you guys can see that's a larger value than both of those. So when I calculate the K value, shouldn't my K value be greater than 1? Wouldn't you guys expect? Because you guys remember, how do you get your K value? Remember what you do? It's the products over the reactants. And if I had a greater concentration of products at equilibrium, won't I have a larger numerator than denominator, and then I have a large number divided by a small number, won't I get a number larger than 1? So I plug them in, and what do I get? 51. So then when I look at this equation, let's say I don't know anything about the equation, someone tells me the equilibrium at that temperature is 51, what do I know? Oh, you know what? When it reaches equilibrium, the atoms are going to prefer to be in this arrangement. I'm going to have a greater concentration of this than that. All right, guys, good stuff. We'll see you next time.